Good morning, everyone. I hope you're all caffeinated and ready for another 2-hour lecture. So my name is Julia Roman-Duval. I'm from the Space Telescope Science Institute in Baltimore, Maryland. And since I wasn't here for the lightning talks, I thought maybe I could introduce myself a little bit. So I work mostly on these days and for the last few years on the dust properties as observed in nearby galaxies. And in particular, if you recall that plot that Danny showed between dust to gas ratio and metallicity, my research group and I have been trying to populate that plot with different types of measurements from far infrared emission, dust extinction, and also interstellar depletions observed in with UV spectroscopy. So that's been, and also I study paths at low metallicity recently with the James Webb Space Telescope. I did my PhD on CO gas in the Milky Way, which is the topic that I'm going to be talking about mostly for this lecture. And I work at the Space Telescope Science Institute, which is not your typical academic environment. I do 50% research, and the other half of my time is spent working on the missions supported by STSEI, which are the Hubble Space Telescope, James Webb, and soon Roman. So if you have any questions about being an astronomer in this type of work environment, please don't hesitate to reach out. It's actually super exciting, super interesting, and there's lots to talk about there. So in this lecture, it's a very broad topic, the cool ISM and star formation. So I'm going to be pretty quick, high level. And my goal here is to provide you with all the references that you need so that maybe later on you can go dig into a particular topic a little more. So hopefully you'll have all the material you need to go check things out and investigate concepts a little further. But my lecture will be pretty high level. Right, and so I will get started. I actually give the title of this lecture, Zooming in on the Physical Processes Driving Star Formation and Galaxy Evolution, because the Milky Way is the environment where we can get the most detail on all the physical processes that happen in the ISM. Those lead to star formation, which we know is the driver of galactic evolution. So we get a lot of detail. Getting the big picture view is a little bit harder because we are embedded in the Milky Way. And as you'll see in this lecture, it's very hard to figure out what the structure of our galaxy is being on the inside of it. And so to get the big picture, actually the kind of studies that Danny talked about is very complementary. So this is the outline of the lecture. We'll start with different traces of the ISM. We've talked about some of those here and there during the summer school so far. I will then go over the different phases of the ISM and then focus on the cool phase, which is the main topic of this lecture. So in particular, we'll go over what we know of the properties of galactic molecular clouds, their distribution in the Milky Way, and not just molecular clouds, but molecular gas in general. Then we'll go over what we know of turbulence in molecular clouds. And Stephanie talked about this a little bit. This is very important in star formation and feedback. And then finally, I'll conclude with linking all of this together and making the link to star formation in the Milky Way. And maybe halfway through, we can take a little break with questions. All right, so we'll get started with traces of the ISM. And this is one of the only extragalactic images I'll show here, but I can't help myself just because it's so pretty. This is the LMC seen in dust and H1. The H1 is in red, the hot dust in blue, and the cool dust in green. So this is one of the other galaxies where we can get quite a bit of detail, but maybe not as much as in our own Milky Way. Anyway, so I'll start with images of different traces of the Milky Way, similar to what Danny showed. On the top left here, you have X-ray from Rosita. Here, I'll use the pointer. So this is the energetic ISM of the Milky Way, and you can see that it has a pretty large scale height, a few kiloparsecs, and depends a little bit on the energy of the X-ray that you're observing. But this really traces the energetic ISM, the hot ISM that I'm not going to be talking about. On the right here, you have H alpha. It's a tracer of ionized gas and mostly traces H2 regions in the Milky Way disk. On the bottom left, you have the 21 centimeter, which traces atomic hydrogen. And so there you can really see kind of the gas, star-forming gas disk of the Milky Way plus Magellanic clouds here and Magellanic stream. And then finally, as you go to the denser and denser ISM, on the lower right here, you have CO emission observed by the Planck satellite. And this really traces the denser molecular ISM. And so now we'll go a little bit more details about what these different tracers mean and the physics behind the ISM traced by those observations. So I'll get started with one of the key tracers of the interstellar medium of galaxies, and that is the 21 centimeter hyperfan transition, which traces atomic hydrogen. 21 centimeter corresponds to 1.4 gigahertz. So this is a spin flip transition where you have the spin of your proton and electrons that can be aligned or anti-aligned. The lower energy level is the anti-line configuration. And so when the spin of the electrons flips from one level to the other, you have a emission of 21 centimeter radiation. And so you can trace atomic gas that way in the Milky Way, which you can see from the H14 pi survey here in the bottom. This is the entire galactic plane and actually goes out to fairly large velocities. And this is what we use usually to trace atomic hydrogen, not just in the Milky Way, but also external galaxies. Then the CO rotational transitions, which probably you've all heard about, trace the molecular ISM. And I'll get into a little bit more detail about this. So carbon monoxide is the second most abundant molecule after H2. You may know that H2 does not have a dipole moment, so it's pretty hard to observe. So usually we use CO instead. These are rotational transitions, which with energy levels that are given by these equations here. This is the moment of inertia for the CO molecule, and then you have quantized rotational levels given by the rotational number J. And so when you have a transition from one level down to the next, so for example, 1 to 0 here, the energy of that transition is given by the J rotational number. So mostly, we use the 1 to 0, 2 to 1, or 3 to 2 transitions. The 1 to 0 is at 2.6 millimeter here, 115 gigahertz. The 2 to 1 transition is at 1.3 millimeter to 130 gigahertz. It's all multiples of 115 basically. And then occasionally people will also use 3 to 2, etc. But of course, as you increase the rotational number that you probe, you trace slightly more energetic temperatures. So we observed the CO rotational transition with ground-based telescopes in the millimeter, like ALMA, which is an interferometer, very high resolution, MOPRA, single dish in Australia, IRM in France, as well as PDBI. But also you can observe the CO line with Planck, given that it's included in the wavelength of some of the filters, and get kind of an integrated intensity image that way. And I should note that there are two isotopes for CO, the 12CO and 13CO. And the ratio in the Milky Way of 12CO to 13CO is given by this equation, which is from the Millam 2005 paper. So at a galactocentric radius of 3 to 4 kiloparsecs, that's about a ratio of 50. And so you would expect the optical depths of the 12CO to be much larger than that of 13CO. All right. Emission lines are not the only trace of the ISM. Of course, we have dust. We've heard about this. Dust absorbs UV optical stellar light and re-emits it in the far infrared. So for a galaxy like Andromeda or Milky Way, that's actually 50% of the energetic output of a galaxy. It's a large number. Dust emits in the far infrared roughly as a modified black body. There are more detailed physical dust models that include shorter wavelengths, but in the very far infrared wavelengths, you can have basically an opacity law that depends on wavelength. And that would be the equation here at the top right, that's the opacity. So your emission in the far infrared, which is here, will be proportional to that opacity, which can have a wavelength dependence, the column density of dust along the line of sight, and the Planck function at the temperature of the dust. And so you end up with an SED that looks something like this. This is, I mean, there are many papers that do dust modeling to get the dust parameters. This is from a recent paper by Chris Clark. And so you can basically model the far infrared SED using those modified black body models and get the temperature and surface density out using some model assumptions. There is model dependency here. So this is better, no? Yeah, okay. Here's a Planck image of dust emission at 150 microns. You can see that dust is everywhere in the ISM, and that's why we use it as a tracer of the ISM, not just in the Milky Way, but also at high redshift, where you can't get the 21 centimeter line, for example. And so I think this is a very important tracer of the ISM, and as we'll see, it can also help us trace gas that is not traced by CO. OH1. So dust emission is a tracer of the ISM, but of course, dust extinction is also a tracer of the ISM. And recently, there's been a lot of efforts to map out the distribution of dust and gas in the ISM using dust extinction. So as I mentioned, dust absorbs UV optical light and remits in the far infrared. That means that you can actually use dust reddening and distance to stars to map out the 3D distribution of dust in the ISM. And so I'll get back to this later, but you can see a schematic of how this works here. So on the left, this is an image of the Milky Way from Gaia. And I believe this is just a stellar density image, but it does pop out kind of the dust lanes in the Milky Way here, which are basically have an underdensity of stars because they are extincted or reddened. So if you know distances to stars from, say, Gaia, for example, and you can also measure reddening towards those stars, then you can actually map dust clouds in the Milky Way, which are also just ISM clouds, from this 3D dust mapping. And this is an example from Leiker et al. 2021. This was a particular example, I think, to map out a molecular cloud near a supernova remnant, but doesn't matter. The schematic works all the same. So you measure distances from Gaia using towards a bunch of stars, right? And you also know the reddening. So this star here is more reddened than this star here. So then you know that there's a dust cloud between distance D4 and D2. And then you can get out of the 3D distribution of dust in the ISM. And if you assume a dust to gas ratio, also gas, and you know where your clouds are. All right, so this was a very brief overview of tracer of the ISM, and it's meant for you to understand what I'm going to be talking about now in the rest of this lecture. So I'm going to jump now to the definition of ISM phases, and then we'll focus on the cool phase of the ISM. So there's heating and cooling in the ISM that set its temperature. And I wanted to go over some of the physical mechanisms that drive heating and cooling, because I think it's important in order to understand what we're going to be observing in terms of the atomic phase, which is split into the warm neutral phase, the cold neutral phase, and then molecular clouds. So the dominant heating mechanism in the neutral ISM is the photoelectric effect on dust grains. So you can have electrons heating, you can have dust grains releasing electrons will collide with gas molecules and heat them up. So you can see the heating rate here in diffuse clouds as a function of the volume density, going from about 1 per centimeter cube to 10 to the 4, which would be dense cores. And you can see that in this range, the photoelectric effect dominates the heating, followed by cosmic ray, which we've heard about already. In the warm neutral phase, at the lowest densities, cosmic rays will dominate, and then photoelectric effect will take over at a density of 0.1 per centimeter cubed or so. And then in molecular clouds, which are well shielded from radiation, right? So the photoelectric effect will not be as important because your radiation cannot penetrate the cloud. Then the cosmic rays take over and dominate over the heating. So different regimes in densities mean different heating mechanisms will dominate. This is meant to be cooling, I think. So this slide is about cooling. So I've plotted here cooling rates. This is from the Drain et al. 2011 ISM book. And if you don't have it, I highly recommend you get it because it has basically all the ISM physics in it. So cooling rate as a function of temperature for the warm neutral phase and the cold neutral phase. I'm going to try to get over that later, but basically think of it as a temperature, different density and temperature ranges. So the carbon-2 fine structure emission will dominate the cooling in a wide range of temperature, and especially at the lowest temperatures. So the C2 158 micron line will dominate the cooling, and then at the highest temperatures, then the O1 at 63 microns will take over. As you go to cooler and denser media, then your C2 will dominate on the lower temperature range, but then again, O1 takes over. So these two lines, O1 and C2, pretty much dominate the cooling in the atomic ISM. Something to remember. So once you know your cooling rate and your cooling curve and your heating rate or heating curves, you can derive what are called phase diagrams. And these are the diagrams from which we define the different ISM phases. So in steady state, you have heating and cooling equal to each other. And so you can relate basically the pressure or temperature in the ISM to the density through these phase diagrams. So here is a phase diagram that so related pressure versus density. This is from the Wolfire 2003 paper. At the lowest densities, so between 0.01 and a few 0.1 per centimeter cubed, you have an increase in the pressure as a function of density, then a decrease, and then it increases again. The stability criterion in these diagrams is that the derivative of the pressure as a function of density needs to be positive. So this is stable, but this phase here is unstable. Above this curve, you have heating that is greater than cooling. Below it, cooling is greater than heating. But the ISM in steady state will be along this curve here. This is for a radius of 8.5 kiloparsecs in the Milky Way. So it does depend on some of the cooling and heating values that you get using cosmic ray flux, some dust density distribution, etc. But this is why we this is where we get the two atomic ISM phases from. So the warm neutral phase is the lower density, higher temperature here. So between say 0.1 and roughly 1 per centimeter cubed. And then the cold neutral phase is on the higher density range, lower temperature range here. There is a hot ionized phase in the ISM that I'm not going to talk about, but you can see where it comes from in this left plot here, which is from a simulation by Hale et al. 2018. So this is a phase diagram. So you can see the warm neutral phase here, the unstable phase here, and then the cold neutral phase here. But on the left here, you have this hot ionized phase that is due to feedback from supernovae and very energetic events in the ISM. So all ionized gas. I'm not going to talk about it, but I think it's important to know that it exists and where it is on this phase diagram here. So to summarize what I just talked about, so these are the different phases of the ISM. So again, the hot ionized medium here, ionized gas is traced by UV, X-ray, and radio synchrotron emission. The H2 gas, pardon me, are H2 regions in the Milky Way. That's what we saw with the H alpha tracer at the beginning of this lecture. It's denser gas, it is denser, slightly cooler than a hot ionized medium, and is traced mostly by line emission, and in particular H alpha. Now, in the atomic ISM, we have the W and M, the warm neutral phase, the cold neutral phase, and molecular clouds. You can see the temperature range of these different phases here. So the WNM has a temperature of about 5,000 Kelvin, mean density of 0.6 per centimeter cubed, and a scale height in the disk of 400 parsecs. And that's traced because it's atomic gas using the 21 centimeter emission and absorption, as well as optical UV emission lines. The CNM is denser and cooler and has therefore a smaller scale height of about 150 parsecs. You can see the dominant heating and cooling mechanisms here. So again, photoelectric effect on dust grains for heating and phi structural line emission for cooling. And then finally, molecular clouds they're not a phase per se, but they are like the densest part of the ISM. So dominated by the H2 molecule, with very cold temperatures from 10 to 50 kelvins, high densities above 100 per centimeter cubed. And then the scale height is yet smaller than for atomic gas at 50 parsecs. So as I mentioned there, the dominant heating mechanism is cosmic rays because they can actually penetrate deep inside the clouds. And the dominant cooling mechanism is actually CO emission in this case, as well as some C1 and C2 to a lesser extent. So how do we probe those different phases and extract their properties? So for atomic gas, as I mentioned, the 21 centimeter line is key, both in emission, but also in absorption. So I actually stole this slide from Claire Murray because it illustrates really well the point here. If you go back to your radiative transfer equations, and if you're not too familiar with them, go to the Rubik-Lightman or the Drain ISM books. When you take a spectrum towards a background continuum sources that emits at 21 centimeter, and you have an ISM cloud intervening along the line of sight, you will get both emission and absorption, right? So this background sources is much brighter than the H1 in the cloud. And so there you will have an absorption with optical depth tau, as well as emission that is attenuated, absorbed by the foreground cloud. On the off position, you're just looking at ISM, you just have emission from that cloud. So what are the unknowns here? How much H1 is there along the line of sight? That's the optical depth of the transition. And what is the spin temperature of the H1 gas? So you have two unknowns, and so therefore you need two equations to solve for those properties. And that's why you do both emission and absorption of the 21 centimeter line to get at both of those parameters. So that's what a group led by Claire Murray and Snezana Steiner-Roach and Charles Dickey, there's a lot more people working on this, but that's what they have spent their careers doing. And the most recent survey is the 21 sponge survey that was able to actually pin down the spin temperature and optical depth for the different atomic phases of the ISM. So the WNM, the unstable phase, and the cold neutral phase. And so these are the results of these studies. And this is all from a paper by Claire Murray 2015. So on the top here, you can see the H1 column density of the CNM, which with the distributions that peaks around 10 to the 19, 10 to the 20. The different histograms are comparisons of different studies, but I think the conclusions are pretty similar. And on the bottom is the column density histogram of the WNM. What you can see here is that 20 to 60% of the H1 is actually in the CNM in terms of mass. 20% of the H1 is in this unstable phase in the phase diagram. Remember when the slope was actually negative? And this could be due to colliding flows in the ISM, right? And so it's very dynamic and transient. But there's a substantial a fraction of the mass of H1 that is actually in this unstable phase. Again, this is a comparison of the fraction of CNM gas from different studies. So the results that I show here are from the 21 sponge survey, but there were other papers looking at this, and I think maybe except for this last one here, had similar conclusions in terms of the fraction of the H1 gas in the CNM. All right, so atomic gas is covered, and now molecular gas. I'm going to focus on molecular gas because this is the fuel for star formation, at least in relatively high metallicity galaxies. So H2 forms on those grains, which act as a catalyst to kind of absorb the energy released by the formation of the molecule. You can see here the energy levels of the different transitions for H2, both electronic. So these are the electronic transitions, vibrational here, and rotational, which is the ladders given by the rotational numbers J here. So what happens is H2 will be excited by UV photons, and so jump from one electronic level to the next. And then it will de-excite. And depending on where it excites in the vibrational levels, it might remain a molecule or get photodissociated. So UV photons will dissociate H2 if they end up in a vibrational level above 14. You can see here, so this is vibrational level 0, 1, etc. Above 14, you are in the continuum. So your H2 molecule will be dissociated. And so that's one. Right, okay, I think that's good for now. We'll get back to this later. So your UV photons will dissociate H2. And so to form molecular clouds, you need to have enough shielding to absorb those UV photons so that the molecule can exist. Here's a very simplistic diagram of a molecular clouds. Molecular clouds are not sphere, far from that. We'll see that later. But for now, this will do. So what you need is you need to have a dust envelope that provides enough shielding to UV photons for H2 to form. So in it, the plot on the right is basically the equivalent of this very simplistic cartoon, but in 1D. So on the left here, on the x-axis, you have the optical depth, so inside the cloud. On the y-axis, you have the fraction of H2. So as you get deeper and deeper inside the cloud, you get more and more shielding from dust and H1. And at this RH2 radius here, you have enough shielding that you can actually sustain a molecular fraction greater than 50% or so. And this is shown here for, I believe, 2 different assumptions on the absorption cross-section of dust. Similar results, though. Now, as I mentioned, H2 does not have a dipole moment, right? It's a symmetric molecule. You have H and H. And as a result, it does not have dipole radiation. It only has quadrupole transitions, which are excited only at fairly large energies, corresponding to temperatures of about 500 K or so. So you cannot see H2 in cold molecular clouds. But what you can see is the second most abundant molecule, which is carbon monoxide. And as a result, CO is widely used as a tracer of molecular gas in the Milky Way and other galaxies, although it does come with challenges, as we'll see in a couple of slides. On this diagram here is from the Bolato et al. 1999 paper, and it kind of illustrates what we expect in terms of the ability for CO to trace H2 as a function of radiation field and metallicity. So at solar metallicity and fairly normal radiation fields, you have a molecular cloud that has an H1 envelope, H2, then H2 without CO, H2 where carbon is dominated by C1, and then CO inside in the dark circles here. As you decrease metallicity, you have less and less dust shielding, less and less ability for H2 to form because the abundance of dust grains, which are the sites of H2 formation, decreases. And so your CO clumps, which are the dark part of the circle here, will shrink because CO will be photodissociated by UV radiation. Similarly, as you increase your radiation field, the same thing starts to happen. H2 does have some self-shielding because it has a lot of, so these electronic levels that I showed before will absorb UV photons, and it has an ability to self-shield. And so it can exist at lower column densities than CO, but CO will be photodissociated very easily. And so the expectation is as you go to high radiation field, low metallicity, you start having those clouds that may have a lot of H2, but the CO core are much smaller in volume. So we lose the ability for CO to trace H2. In the Milky Way, that is not too big of a concern, but I just want you to remember that at lower metallicity, the assumptions that we use in the Milky Way start to break down. This is an illustration of this point using simulations that include hydrodynamics and chemistry. These are from the Glover and Clark paper. So similar to the previous diagram here, but now molecular clouds aren't spheres anymore, right? These are actually simulations. So on the top panel, the top panels show a constant radiation field that is roughly the same as in the solar neighborhood, but decreasing metallicity. So you go from solar metallicity to 0.5 solar, which is kind of the LMC, to 0.2 solar. The pink contours show the H2 surface density. The color scale is the CO. As you go to lower metallicity, you can see that you start eating away at those CO clumps. And you end up with a lot of gas that is H2, but not traced by CO. And similarly, as you go to higher radiation fields, so this is 10 times the solar neighborhood radiation field, varying metallicity. If you compare, for example, for the Milky Way, you would compare the top and bottom left panels. So radiation field of 1 times the solar neighborhood versus 10 times, you can see the effects of radiation field on the structure of CO gas with respect to the H2. And so as a result, you would expect a varying CO to H2 conversion factor, which is also called XCO. So XCO is the column density of H2 divided by the integrated intensity of CO. And in the solar neighborhood is about this number, 2 times 10 to the 20 centimeter per centimeter square per Kelvin per kilometer times second. You can also express this in surface density units with the alpha CO parameter, which would be 4.3 in those units. So because of the effects that I just described, the H2, the CO to H2 conversion factor depends on the environment. So on the left here is a plot from Bolato et al. 2013 showing this alpha CO, which is equivalent to XCO, as a function of metallicity. And so the solar neighborhood and Milky Way would be somewhere around there. And you can see that a constant factor starts breaking down as you go to lower metallicity. And the same is true as you increase radiation fields as well. So something to keep in mind, again, not critical for Milky Way studies, but I think it's important to realize that when we trace the molecular ISM with CO, there are some assumptions that go into the results. So there is CO dark gas in the Milky Way. Even though we're at solar metallicity, right, you still have those molecular gas envelopes that are where H2 is not photodissociated, but CO is. And so how do we trace that gas? Well, one way to do this is using dust as a tracer of the ISM. This is why as I said before, dust is a very important tracer of the ISM because, for example, it allows us to trace that CO dark gas. So this was done using Planck. So Planck, measured dust emission at 350, 800, 550, and 850 microns. So from that, you can derive a column density of dust. Then you can assume a dust to gas ratio that is typical for the Milky Way. So you get your gas mass. You also have H1, and so you can do gas minus H1, and you should get what is H2, right? Because the neglecting ionized gas, which at those column densities is very negligible. And so this way they were able to trace CO dark gas. And you can see this in the right plot here, where you have the optical depth at 545 gigahertz as a function of the total column density of gas. And there's roughly a linear relation that is shown by this red line here. But you can see that the measurements start to deviate from this linear relation right around there. So at column densities from roughly 10 to the 21 to 10 to the 22. And this difference between this linear relation here and the measurements is due to CO dark gas, where the CO dark gas is emitting in the dust. So you have a small excess, but it's not traced by regular gas tracers like H1 and CO. So here's a map of this CO dark gas with column densities going from 19 to above 21. So it's not negligible. It's not a small fraction of the ISM. And it's, mostly, it's very extended. And I think from the Planck mission, they measured a CO dark gas fraction that was over 100% of the gas that we can actually trace with CO. So in other words, you'd have twice as much H2 as you would measure from CO alone. I should caution these results assume a constant dust to gas ratio, and that's a key assumption. If the abundance of dust changes with environment, for example, if dust grows in the ISM, which I think we do have good evidence that this is happening now, then you would predict a higher fraction of CO dark gas than is actually there in the ISM. So another way to quantify the CO dark gas in the Milky Way is using the C2 emission. So carbon-2, carbon in molecular clouds is dominated by CO in the denser cores. But as CO is photodissociated in the envelopes of molecular clouds, that carbon is present in the form of ionized carbon, or C2. And so you would expect to be able to trace this CO dark gas using C2 emission at 158 microns. And this was done in a couple of papers, in particular Velusamy in 2010. And they found that basically the ratio of H2 traced by C2 to the ratio of H2 traced by CO is roughly 40% on average. Simulations that include chemistry as well as radiative transfer predict that about 30 to 50% of H2 should be CO dark in the Milky Way. And this was obtained by Wolfire et al. 2010 using analytical models, as well as Smith 2014 using simulations. So we have, an estimate based on dust that is about 100% of CO dark H2 with the assumption of a constant dust to gas ratio that might actually overestimate the fraction of a CO dark H2. And then C2 based measurement give us about 40%, which is consistent with what models predict. So I think the truth is probably somewhere in between, which means that, in the Milky Way, when you use CO to trace your molecular clouds, be aware that you're probably missing a small, a significant fraction of molecular gas that is not traced by CO. So some of the questions in this field that I think remain unanswered is what is the fraction of H1 in this unstable phase that I described? So depending on the paper, the fraction of the H1 in unstable phase can vary by a factor of a few. So I think this is really an open question. It's a hard measurement. You need to get lots of sightlines in 21 centimeter in both absorption and emission. How much CO dark H2 is there? That's a question that's actually I've been trying to tackle using dust, H1 and CO measurements combined, and there's some circularity there. So I think this is far from being a solved problem. How does the fraction of CO dark gas vary with environment, and in particular radiation field? So in the Milky Way, you have a fairly wide variation in radiation field, depending on whether you're near a star-forming region with lots of ionizing photons from O and B stars, or a more quiescent environment like Taurus, for example. And so, how does the fraction of the CO dot gas depend on the kind of environment that you're in is an open question. And then similarly, how does the XCO factor to convert from CO to H2 vary with environment and with spatial scale? When you have a large beam or you average on large spatial scales, you're basically averaging, pixels that are bright in CO surrounded by CO pore envelopes. Whereas if you're very high resolution targeted on a molecular cloud, you might not do that. So I think there's a spatial scale dependence that sometimes we forget about here that is important, not just to measure the H2 mass in the ISM, but also to interpret the measurements that we get from CO. All right, so having described the different phases of the ISM, mostly H1, the warm neutral phase, the cold neutral phase, the unstable phase, and the different traces of the ISM, I will now focus on the properties of galactic molecular clouds. And after this, we'll take a break and ask questions. So I'll start with the formation of molecular clouds, which is actually a very open question that is currently very much addressed by simulations as opposed to observations. There are different hypotheses for the formation of molecular clouds, and the truth is probably a combination of all of those. You can have localized converging flows. So for example, if you have bulk motions that collide or supernova explosions that push the gas outwards in the ISM, you can have those converging flows that where at the interface of which gas is compressed, the densities are increased, and you can actually form molecular clouds. Another scenario is cloud-cloud collisions in spiral arms. This was simulated by Claire Dobbs in a series of papers around 2008. This seems to be a dominant mechanism for low surface densities. So as your gas travels through the spiral arms, you have some crowding that occurs, and little pockets of gas collide together and grow. And you can see this actually on the right side here, where the simulations can follow parcels of gas, and they are actually traced by the different dashed lines here. This is molecular cloud number, I don't know, I don't remember from the simulations, but you can basically follow it as a function of time. And you can see that this cloud-cloud collision actually plays a big role in the formation of molecular clouds in or near spiral arms. Gravitational instability is another way to form molecular clouds, and this is to be a dominant mechanism at high surface densities. Also combined with, of course, with cloud-cloud collisions. You have the magnetogene's instability, and I'm not going to talk about that. Parker instability, and observations and simulations seem to suggest that the lifetime of molecular clouds are relatively short, so 20 mega years or less. So this is, well, we know very little about formation of molecular clouds, but these are some scenarios that seem to be the most likely explanation for how these molecular clouds form. Now, I wanted to give a bit of history on the observations of molecular clouds in the Milky Way, which started in the 1970s, early 1970s, actually with detection of H2 in the UV using absorption line spectroscopy by Carruthers et al. Shortly after, CO emission was detected at 2.6 millimeter by Wilson. He actually wrote a very good book on millimeter astronomy that is, I don't know, it's a go-to for me. So if you always have questions about how to convert your CO column densities from CO1 to 0 or 2 to 1 integrated intensities, this has all the math in it. Great book. Some of the first surveys of CO in the Milky Way included one by Burton et al. 1975, and then Dame et al. 1987. You can see that we've gone a long way since then. This is an LV diagram, so galactic longitude on the y-axis, velocity on the x-axis from Burton et al. 1975. It covers longitudes going from 0 to 180. So it's pretty good chunk of the galactic plane. And you can start to see some structures there, but the resolution of and the depth of the surveys cannot really give you a lot of details on the distribution of molecular gas in the Milky Way. However, they were able to pull out the radial distribution, assuming an axisymmetric disk, which is peaking around 5 kiloparsecs away from the galactic center here. This is why this region of the Milky Way has been known to be the molecular ring. Is because there's really a peak in CO emission at this location. In 2001, Dame et al. Actually performed the first highish resolution large-scale CO survey in the Milky Way. This was at 4 arc-minute resolution using the 12 CO 120 line. And it really revealed the structure of molecular gas in the Milky Way in way more detail than had been possible before. Yoda et al. 2010 surveyed a similar area with both 12 CO and 13 CO 2:1 at similar resolution. And both of these surveys are very complementary because one is the 2:1 line, the other is 1:0. So it gives you some constraints on the excitation of the CO molecule. And here you can see again a velocity longitude diagram of CO emission from the Dame survey. So you can pick out some features already, the galactic bar, some spiral structure here, or perhaps pole structure. We'll see. This is also a matter of debate. And at the bottom here is the corresponding galactic longitude latitude. So just an integrated intensity of CO in the Milky Way, with a galactic center being around here and most of the CO emission inside the solar circle, so within the smaller longitude range. Now, the survey that showed we still had resolution of a few arc minutes, which is not quite enough to get the detailed structure of molecular clouds, which have sizes of, a few parsecs to maybe a few tens of parsecs. And so it wasn't only until we had higher resolution, so, tens of arc seconds, 30 arc seconds, for example, that we were able to really pin down the detailed structure of CO gas in the Milky Way. One of the surveys that did this is the Galactic Ring Survey, or GRS, which observed the range of galactic longitude from 18 degrees to 54 degrees in a 13 CO 1:0 line. There was a similar survey in the Outer Galaxy published by Chris Brunt et al. 2015, which got both 13 CO and 12 CO 1:0. And those two surveys were very complementary. You can see here a galactic longitude velocity diagram of the GRS. Again, showing a lot of detailed structure. All of those are individual clouds from which we can actually constrain the properties of molecular clouds more accurately. So this is a summary of all the CO observations of the Milky Way done since the 1970s. And this is a compilation that was done by a review by Mark Heyer. Again, a good reference to get an overview of the molecular cloud properties in the Milky Way. So as you can see, this field kind of started in 1970. I already mentioned that. But in the 2000s, I would say the spatial extent coverage as well as the spectral coverage, so 12 CO, 13 CO, 1:0, 2:1 really increased. And so I would say since 2000, there's been really a boom in the field in terms of characterizing the properties of molecular gas in the Milky Way. So this is all well and good. We have CO observations, but now how do we segment or break down these position velocity cubes into actual molecular clouds? That's a very tricky business. So, and I'm saying position velocity because what you get is basically an emission line spectrum, CO, for each position on the sky that you probe. So you have P, P, and V. These are the 3 dimensions that you have. So you can use algorithms like ClumpFind to actually segment the emission in the cube into individual molecular clouds. Again, in LBV space. ClumpFind is using basically isobrightness contours that are related to each other to identify molecular clouds. So these are contiguous emission features. It doesn't assume any shape or anything. And here you have again the same velocity longitude diagram with the CO emission and the result of the clump-fine segmentation. The ellipses are just to indicate the location. The actual individual molecular cloud cubes are not, it doesn't assume any shape, elliptical or anything. It's just to kind of map out and visualize the location of those clouds. Now you can see that one of the issues with this is that, first of all, the size and mass of the molecular clouds that you identify that way will depend on the sensitivity of your observations, right? Because you use contours in your emission to identify molecular clouds. And second, it does not capture the entire emission in your PPV cube. And so oftentimes you'll have diffuse emission that is left out and not identified as part of a cloud. So that is one limitation to segmentation. But when we have to look at the properties of molecular cloud, we can't get around this kind of segmentation exercise. Another method to actually extract individual molecular clouds from CO emission cubes is the dendrograms. So there's a quote here from the Eric Kozolowski, who pioneered this method. Dendrograms represent the essential features of the hierarchical structure of isosurfaces in molecular clouds line data cubes. So basically, you have an emission line cube here that's on the left with various level of brightness. And of course, the ISM being hierarchical, you're going to have denser, brighter clumps surrounded by more diffuse CO envelopes. So the dendrograms will identify the leaves, which are like the densest part of the emission, the brightest part of the emission. And these are in an island of surrounding emission that will be associated with the branch. And then finally, these are brought together because they are inside an isosurface contour as the root. So this is a schematic. On the right side here, you have an actual application of this method from the Rice et al. Paper that uses the DAME 2001 survey. So you can see the CO emission in longitude, latitude space. This is an integrated intensity image, and the different components, leaf, branch, and root of the dendrograms. So you can see it does a pretty good job at capturing the emission, does leave some diffuse emission out. Again, that's always a limitation. But it also allows you to track down the hierarchical structure of the ISM by relating the leaves, the branch, and the roots together for different components. And then finally, the third method that's been used in the literature to extract molecular clouds from CO emission cubes is the Gaussian decomposition. This was done by Miville Deschênes 2017 using the DAME survey, so the entire galactic plane. And basically, they decompose the CO emission, which you can see an example of here, in Gaussian components of a given velocity center and width. And that way, they were actually able to capture 98% of the emission in the cube. So as far as I know, this is actually the algorithm that captures the highest fraction of the emission without leaving too much diffuse out. So once you have segmented your CO PPV cube into individual molecular clouds, you can start looking at properties of individual objects and look at the statistics of this population as a whole. So I'm sorry for the equations, but I feel like it's useful to have them in hand. If you need, maybe later you can download the slides and you'll have the references of where to go to basically convert your CO brightness temperatures into excitation temperature, optical depths, column density, mass, etc. So I'm not going to dwell too much about this, but basically when you have 12 CO data, I think I've mentioned that 12 CO is optically thick, so optical depth much greater than 1. And that means that you can use the brightness temperature of your 12 CO emission to trace the excitation temperature of CO as a whole, also accounting for CMB radiation. The 13 CO optical depth is much lower. The abundance ratio between 12 CO and 13 CO, as I said, is somewhere around 30 to 70, depending on the location in the Milky Way. So your 12 CO is optically thick, but your 13 CO oftentimes will be optically thin. And what that means is it's a tracer of the column density of CO along the line of sight. So using your excitation temperature that you get from 12 CO, you can then derive your 13 CO optical depth. And once you have optical depth, you have column density, and therefore you can get mass. And this is given by this equation here. One key point to remember is that to get your mass, you have to know the distance, right? No, the column density gives you the amount of material on the site, but if you then want to have the mass of your whole object, you have to integrate over the surface of the molecular cloud, which will depend on distance. And distances are tricky, as we'll see. So assuming you know the distance, and we'll see how we do that later, you can then, inside your isophote, so basically the mask of your molecular cloud that you got from your segmentation algorithm, you can get the radius. And usually what we do is we take the spatial extent in longitude, latitude for a molecular cloud, multiply by distance squared and the number of pixels, and you get your area. Once you have your area, you can compute an equivalent radius by divided by pi, just assuming a circle. This is really an effective radius, not molecular clouds are not spherical. You can compute what we call the virial parameter, which is the ratio of kinetic energy to gravitational energy in a molecular cloud. And if you do a few conversions, basically scales as the velocity dispersion in 1D, the radius, and inverse mass. You can also calculate the surface mass density, which is simply the mass divided by the equivalent area of the molecular cloud. And again, this all assumes that you know the distance, right? So now we're going to talk about how we get distances to molecular clouds, which is actually very tricky because we are embedded in the Milky Way. And our observations of CO are basically position, velocity. We do not have the third dimension along the line of sight. So there's several methods that we can use to estimate distances to molecular clouds. Some of them have to be applied to individual objects. And so it's pretty tricky when you look at large samples of, 700-800 molecular clouds, as was the case for the galactic ring survey. But one method you can use that's actually very efficient because it can be done directly, automatically, I would say, is kinematic distances. So this is the Milky Way disk, is the galactic center, and then you have molecular clouds orbiting around the galactic center, say, at a velocity that is equal to that of a rotation curve that we more or less know. For example, from Clements 1985, there are more and more recent ones. But if you know the velocity, the rotational velocity as a function of galactic centric radius, you can actually relate the radial velocity of your molecular cloud to its distance. And using these equations, I know it's a little complicated. Basically, as you increase the distance here, so right, the molecular cloud is going in this direction using the rotational rotation curve. You're looking at an angle equals to the galactic longitude compared to the galactic center, right? And you're measuring the radial velocity of a molecular cloud. So there's some projections between the rotation curve, the angle, the longitude, and the radial velocity you're measuring, but basically you can all relate it. And so as you increase the distance of a cloud from 0 to, let's say in this plot, only 25 kiloparsecs, which gets you pretty much way far away from the galactic center, you see that your radial velocity will increase. It will hit what we call the tangent point here, where you're basically looking perpendicular to the axis of galactic center to your molecular cloud. And then we'll start decreasing again to negative velocities. So if you can measure the radial velocity of your molecular cloud from the CO line, right, you measure something along this dashed line, and then you can tell at what distance it is, except you have two solutions, a near and a far distance. That's called the kinematic distance ambiguity, and that's been a nagging problem in CO studies because radial velocities are really easy to measure, right? You have your line, it's a radial velocity, but then you don't know if it's at a near or far distance. And of course, it's on either side of the Milky Way disk. So these are very different distance solutions. So how to resolve this kinematic distance ambiguity? One way to do this is actually using H1 self-absorption. In this case, so H1 is everywhere in the Milky Way, right? If your cloud is at the near distance, it's a cold cloud, H1 is cold, temperature of 10 Kelvin or so. At the far distance and at the same velocity, you're going to have warm H1 emitting 21 centimeter radiation. As this 21 centimeter radiation travels to us, it passes your cloud that is at a near distance, and therefore there will be self-absorption in the H1 spectrum. So what you're going to see is CO emission at a given velocity, and then in the 21 centimeter spectrum, you're going to have this self-absorption feature. So H1 self-absorption means your cloud is at the near distance. If your cloud is at the far distance, there is no emission at the same velocity at further distances to create any kind of self-absorption. So in this case, you do not have any self-absorption. So by comparing your CO spectrum to your H1 spectrum and identifying self-absorption features in the H1 spectrum, you can actually figure out whether a molecular cloud is at the near or far distance. This method works really well. The problem is it cannot really be automated because the H1 spectrum is so complex. And so it has to be done manually for clouds individually. So just to illustrate the challenges of this method, here's an actual real life comparison of CO and H1 spectrum. So here's an example of a cloud at the near distance. The solid line is the 21 centimeter spectrum. The dashed dotted line gives you the CO spectrum. And then the dashed line is an H1 spectrum on a slightly off position, just to give you an idea of what the actual 21 spectrum in that area looks like. The 21 centimeter spectrum is not smooth. It's full of little features that could be mistaken for H1 self-absorption. And so that's why we take an off position. So in this case, you can see that at the location of the CO emission, there's actually a dip in the on spectrum for the 21 centimeter. That's not in the off spectrum. That's a self-absorption feature. So this cloud is at a near distance. Here's an example where the CO emission is not associated with any H1 self-absorption feature. You can see the on and off spectra here don't have any dips. That cloud is at the far distance. For the GRS survey, there were something like 500-700 molecular clouds, and we had to do this one by one. So it was a very time-consuming exercise that cannot be done for very large samples of molecular clouds. And that's why people have been developing other methods to try to get distances to molecular clouds. For example, maser parallaxes. So when you have a massive star-forming region, you can have masers, which are basically like lasers, but in the radio wavelength range. Those can be observed to very large distances, again, because they're at very long wavelengths. The Milky Way is transparent, and so you can go out to several kiloparsecs, no problem. Just like Gaia does parallax in the optical infrared, maser parallaxes are just like that. You measure your parallax at the two orbit points of the Earth, and your distance is basically 1/p. So you can get really good distances from maser parallaxes towards star-forming regions. And then what you have to do is associate your maser, which is your massive star forming, with the parent molecular cloud, and assume that the distance to your maser is that of the cloud that you see in CO at the same velocity. So Reed et al. Were a pioneer of this method. And on the right here, you can see a map of, I think these are method masers on the galactic plane with really good distances, and attempt at mapping out spiral arms from overdensities in star-forming regions on the galactic plane. This is very effective and actually much more precise than kinematic distances. But measurements are difficult, especially if you're trying to get large samples. Okay, another method to try to get distances to molecular clouds, which I've already hinted at early in the lecture, is 3D dust mapping. This is more recent because it really heavily relies on Gaia. So knowing the distance to stars from Gaia, again, from parallaxes, and using reddening towards those stars, you can actually map out the 3D distribution, not just in individual clouds, but in the entire Milky Way. And so you should go check out the Grid et al. Paper for this method. You can see here the resulting cumulative reddening map between 0.5 and 1 kiloparsec. So it's pretty high resolution in the position on the sky. And then on the right here, you can see a face-on view of the 3D dust map out to 2 kiloparsecs. So works well. Again, the distance resolution is being actively improved by those groups. It's still probably not enough to resolve molecular clouds along the line of sight, but at least you can map out the features in the 3D dust maps to the features that you see in CO and infer the distance to your CO clouds that way. All right, so if we know distances and we have our CO clouds segmented from PPV cubes, we can get now to the properties of molecular clouds. And these are the results of a series of papers that I and others published about 10 years ago. I just want you to get not the details, but more of an intuition of what those molecular clouds are from these histograms. So in terms of radius, it's basically a few parsecs from between one, the left hand here is really limited by the sensitivity and distance bias in our observations. The farther the cloud, the less we are able to resolve small clouds. So I wouldn't pay too much attention, but basically power law distribution function in radius going out to a few tens of parsecs. The mass is roughly 10 to the 4, 10 to the 5 solar masses. So these are, fairly massive interstellar clouds. And usually a power law on the high mass end that has been measured between 1.5 and 2. They have densities of a few hundreds of centimeter cubed. The peak here in this study, as seen by 13CO, again, that's, it is one tracer we can use, but depending on what tracer you use, you might get different numbers. 13CO is a tracer of, not dense gas, but it's also biased towards higher densities compared to, say, 12CO, which can capture more diffuse emission. So in 13CO, the mean density that we see is about 200. Velocity dispersions are anywhere from 1 to a few kilometers per second. The virial parameter, which again is the ratio of kinetic to gravitational energy, is around 1.5 to 1. And the surface density of molecular clouds is, depending on the studies, somewhere between 100 and 200 solar masses per parsec squared. Just for comparison, this is a study that was done by Miville-Deschênes et al. Using the DAME survey, so the entire galactic plane. And they found roughly similar results, but with the kind of striking differences between the inner galaxy, so inside the solar circle, and the outer galaxy, which are shown in blue and yellow. So you can see in the inner galaxy, which is the same range as the GRS, for which I just described the results, you have surface densities approaching 100 solar masses per parsec squared. In the outer galaxy, molecular clouds are much more diffuse with, on average, surface galaxies of just a few solar masses per parsec squared. The mass distribution exponent is -2 in the study, so pretty similar to what was done using both 12CO and 13CO. Radii 10 to 100 parsecs, again, similar to the previous slide, and volumetric densities, number densities of a few tens to 100 or so. Again, outer galaxy, molecular clouds are more diffuse than inner galaxy molecular clouds. And we'll see this is related to the overall distribution of molecular clouds in the Milky Way as a whole. There's a very interesting relation that was found between the mass of molecular clouds and their radii. And that's actually not just interesting, but very useful. So when we plotted the mass of all the GRS clouds as a function of their radii, we found this really tight power law relation with an exponent of 2.36. There's some more theoretical papers that interpret this as a fractal dimension of molecular clouds. So if you had basically a solid disk, you would expect the mass to be basically surface density times r squared. Here our exponents is 2.36. And so that means that those molecular clouds have some fluffiness to them and a fractal dimension that is not 2 and not 3, but in between. If you want to read more about this, there's a paper by Elmer Green and Falgaron in 1996 that explains it all. The useful part of this relation is that masses can be hard to derive. In particular, it's better if you have both the 12CO and 13CO isotopes, because then you can constrain the excitation and column density. If you just have 12CO, again, it's optically thick, so you have to rely on the CO to H2 conversion factor, the XCO factor. And that is less accurate. But if you can measure this relation, and then you can measure, say, a radius from the 12CO emission without having to rely on the XCO factor to get the mass, then you can use this to estimate the mass of molecular clouds. And that's been done in the Milky Way to increase the sizes of samples, because sometimes you just have access to the 12CO line, and if you use this, then you can get more accurate masses. So I cannot not talk about the Lawson's relations. So these have been the topic of many, many papers that focus on the CO properties of molecular clouds. In 1981, Lawson compiled measurements of the sizes, masses, and luminosities of CO clouds from limited literature and found three results. Number one, he found that the surface density of molecular clouds was about constant. Number two, he found the size line width relation, which is basically a parallel relation between the velocity dispersion of molecular cloud and their size or radius. The exponent of that relation is 0.38, and we'll see later why that's relevant. And third, he found a relation between the velocity dispersion of molecular clouds and their mass with an exponent of about 0.2. The interpretation of this sign line width relation is that the motions in molecular clouds are intrinsically turbulent, with velocity dispersions that are greater than the speed of sound, and cascading in a self-similar nature, right? So as you increase the spatial scale, you increase the velocity dispersion with the power law. That's the definition of self-similarity. So later on, other authors expanded on this kind of studies and added many, many measurements. So this is a compilation from Higher et al. 2015, which includes clouds from the galactic center from OCA 2001 paper, clouds from the DAME 1986 survey, which probed the longitude range from 12 to 60 degrees, clouds from the Solomon 1987 paper, which was covered 8 to 90 degrees in the galactic plane, and then a more recent survey by Mark Harry himself in the outer galaxy. So for all the samples, you can see here velocity dispersion on the y-axis, molecular cloud radius on the x-axis, and it's not a great fit. There's a lot of scatter, but basically in all the samples, there's a slope of about 0.5 in the size line width relation. So between velocity dispersion and radius. You can see that depending on the sample, the 0 point of that relation can vary quite a bit. So in the galactic center, right, the velocity dispersions are much, much higher than, say, in the outer galaxy, which are the black points here. And that has to do with the level of steering, of turbulent steering in those molecular clouds. So what does this mean? So I'm gonna, from the Lawson's relation, right, there was a lot of work to try to get at the equipartition of gravitational to kinetic energy. The turbulence, velocity dispersion, is often interpreted as providing support to molecular clouds. Of course, you know, their molecular clouds also affected by gravity. And so if you try to do a virial analysis on molecular clouds and look at the ratio of the two, then you can see that the kinetic energy will be again given by the velocity dispersion here. Gravitational energy, assuming some symmetry, some geometry, is given by this equation, and then your virial parameter is the ratio of the two, and it's given by this. Now, if you assume that molecular clouds are in virial equilibrium, then your velocity dispersion should be related to the surface density and radius with the power 1/2. And you can see basically sigma v over square root r on the y-axis here, which should be, if virial equilibrium is true, proportional to the square root of the surface density, and then which you can see on the x-axis here. So basically, this relation here is this line. And there's a couple of things you can get from this plot. Number one, the surface density of molecular clouds is not constant, as was first observed by Lasson. Actually, there's quite a bit of variation. And you can also see that molecular clouds don't actually lie on that line. The slope is similar, but they lie higher. So what does that mean? If you interpret this in a virial equilibrium context, it means that your masses is lower than the virial mass, and so your clouds are not gravitationally bound. There are other interpretations to this. And that other interpretation is free fall. So there was a paper by Ballesteros Paradis in 2011 that actually pointed out that if you calculate the velocity dispersion that is due to free fall, then that line actually only lies a square root 2 factor above the virial equilibrium line. And that's a very, very small difference. And so basically, whether you're in free fall or virial equilibrium, you're roughly in equipartition of gravitational and kinetic energy. In the case of free fall, the kinetic energy is not providing support to the molecular cloud, but is actually a result of collapse only, right? And so this really points out the need to separate the different components of the kinetic energy. You can have expansive components or compressive components or just rotational components. And these components will not play the same role in the gravitational equilibrium of molecular clouds. One can one can trigger collapse, the other provides support. But you don't know just from velocity dispersion alone. So continuing on this virial parameter and kind of virial analysis of molecular clouds, this paper by Kaufman et al. 2013 actually compiled more samples of virial parameter measurements, not just in molecular clouds, but also denser substructures. So here's the virial parameter in the y-axis, mass on the x-axis for several samples in the literature, some from the galactic ring survey here, the outer galaxy, and the Solomon samples here. The red points here are cores in the Perseus. The purple points are denser structures identified in the Atlas-Gal survey. And they actually trace with dense gas tracers. So this is a kind of a mix and match of a wide range of types of objects, going from just molecular clouds to denser cores traced by dense gas tracers. And what they noticed is that there are many, many clouds with virial parameters lower than 1. And so the interpretation is that either you need magnetic field to help support the molecular clouds and prevent collapse, or you have rapid collapse, which they point out could explain the absence of high mass starless cores. So unclear, and I haven't talked about magnetic fields, but obviously magnetic fields are there in the ISM. And I'm just going to say for now that they should provide some support to molecular clouds depending on the magnitude of the magnetic field compared to, I guess, gravity. But I'm not going to talk about this too much. All right, so going back to the Higher et al. 2015 compilation. So now, if you recall, here, let me just go back real quick. What we were plotting before is velocity dispersion as a function of radius with a relation between the 2 to the power 1/2, which we would expect from virial equilibrium, right? So now we can plot velocity dispersion divided by radius and surface density to try to gain at kind of the normalization of this relation, right? And now all these clouds kind of lie along a much tighter relation than before. Again, the yellow points are the galactic center. The black points are the outer galaxy, and these are inner galaxy molecular clouds in blue. A virial parameter of 10 is the top dashed line here. This is a virial parameter of 3, and the solid line is 1. And you can see that most clouds lie somewhere between 1 and 3, basically. So they would be gravitationally unbound on those scales. And again, I'm talking about scales of molecular clouds as a whole, not substructure that may be collapsing inside molecular clouds. So if you interpret this as kinetic energy playing a support role against collapse, then you would say that these are unbound. But again, kinetic energy is a little tricky because you have some modes that are compressive, some modes that are not compressive. And so this is, I would say, an interpretation. So open questions in this field are, how do molecular clouds form in different galactic environments? I would say that we really, this is a very hard observations to make. So simulations are very helpful, but I think in the future, we will be able to map out gas flows in and around molecular clouds to try to better understand the formation mechanisms. And it may vary with the environment, depending if you're in a galactic center or interarm or spiral arm environment. What are the lifetimes of molecular clouds? Again, hard to probe with observations. How do we get accurate distances to molecular clouds? As I said, the method that we have now come with big challenges and different ranges of applicability. How do we statistically characterize molecular clouds without a subjective segmentation method, right? We saw several algorithms to turn your emission as a whole into individual clouds. They often cut out diffuse emission, which may bias the properties that you measure. So how do we get the statistics without relying too much on the subjective methods? And then how big of a role does turbulence versus gravity versus magnetic field play in the formation of and evolution of molecular clouds is another open question. I think we should maybe take a small break for questions now.
Right. We have 40 minutes left.
I think that's fine, yeah.
Okay. How much time do you want to leave for questions?
Let's do like 5 minutes and we'll do the bulk at the end.
Okay. The bulk at the end.
Yeah.
Any urgent questions? Yes.
I was wondering, so you were showing in the end for the variparameters in the galactic center is very large.
Yes.
But also most of the star formation is happening in the galactic center. But they're not collapsing to, I guess I'm trying to.
Yeah, so the velocity dispersion towards the galactic center are very high. Obviously, the density of gas is also very high. But we know that actually the star formation efficiency, so the amount of stars that you form per unit gas mass in the galactic center is actually fairly low. For the amount of gas that you have in the galactic center, the amount of stars that you form is lower than in the rest of the Milky Way.
I see. It's just more clouds, so the way have more stars forming, but the clouds are not forming stars efficiently because of the.
Exactly, because of the stirring.
Okay, thank you.
Any other questions? Yes. Could you pass it?
I was wondering about this molecular ring. So you showed that the CO emission has this peak, and I was wondering where this might come from, and also how do we know that it's not a selectional effect because we are also roughly at the same distance?
So the sun is located at 8.5 kiloparsecs, so we're a bit on the outside of that. The 5 kiloparsec ring has been observed in a relatively narrow range of galactic longitude. So it's just a small chunk here. Actually, yeah, I'm gonna be talking about this in a minute, but basically, you know, when we have surveys, they don't, except for the DAME survey, they don't cover the entire galactic plane. So it may be related to actually the spiral structure of the Milky Way. I think it's also the there's definitely a radial dependence as a whole, and the two are combined. So it could be either of those, right? But there's definitely an enhancement of molecular gas, say between 3 and 6 kiloparsecs.
It seems like from on and off analysis, it seems like you identify the molecular cloud like structurally,
Mhm.
like in PPB cube. How do you actually find those structures?
You mean in PPP or in PPV?
PPB.
In PPP, yes. Well, you
PPV.
don't. PPV.
Oh. Yeah.
Yes, so so PPV, you have this you use the different algorithms that I explained. So it can be Clumfine, which basically looks at 3D contours in your emission and tries to get the isophotes that are connected together. You have the dendrograms, where I mean it's similar, except that you can actually track the hierarchical structure with the, you know, which cloud do the brighter structure belong to. And then you have the Gaussian decomposition, where along each line of sight, you basically decompose your spectrum into Gaussians. And then you have to use some cluster algorithm to match them together into actual clouds. So there's different algorithms. As I said, the limitation for them all is that you tend to, because you work with contours, you tend to leave diffuse emission that is below your lowest contours out. And so those would not be included in any property you derive for individual clouds. Thanks.
If we want to leave 10 minutes for questions, we need to wrap up.
Okay, all right. So I'll go quickly over this, but so far we've dealt with individual molecular clouds as a population, and we've seen some statistics on this. Now I just wanted to go quickly on the distribution of molecular gas as a whole on the Milky Way, without breaking things up into individual clouds. So you can do this using some of the same tools that I've been talking about, using surveys that, you know, cover the entire galactic plane, like the DAME 2001 survey. So that only looked at 12 CO, so you do have to use your 12 CO CO to H2 conversion factor. But even when you do that, you get a good idea of basically the radial dependence of the surface density of H2 from CO, but also from H1 from 21 centimeter in the galaxy. And so you can see here how this dependence goes. This is from Viville-Deschênes 2017. And so here you can see this was your question, the 5 kiloparsec enhancement in molecular gas. So H2 would be the black points to follow here. So of course at the galactic center you have very high surface densities. And then decreases, and then there's an enhancement at 5 kiloparsecs, and then things obviously go down as you go away from the center of the galaxy. And again, that's why the outer galaxy, which should be beyond 8.5 kiloparsecs here, is much more diffuse in CO than the inner circle, which is up here. So this plot is in log space. You have the corresponding version in linear space here, where you can really see the enhancement of CO emission molecular gas at 5 kiloparsecs. And in the outer galaxy, things are much more diffuse by a factor of several. So again, I think I'm going to skip that. These are just the individual clouds from the Viville-Deschênes study. But I did want to go now. So what I've shown before was based on 12 CO, and again, you have to assume a CO to H2 conversion factor. If you want to do things in a bit more detail, you need 12 CO and 13 CO, so you can really probe the excitation and the column density. And so you can use a combination of surveys, like the outer galaxy survey, which has these two chunks of the outer galaxy survey. The GRS is the red triangle here. And then there was a thrum survey in another quadrant here by Peter Barnes. So if you have good resolution, then you can really quantify the mass of CO gas. I'm going to skip that. This is, again, trying to extract emission from noisy cubes. You can actually separate gas that is traced by 12 CO and 13 CO, which is denser CO gas, versus traced by 12 CO but not detecting the 13 CO, which is more diffuse molecular gas. That's important because this more diffuse molecular gas might not be forming stars, whereas the denser gas is contributing to star formation. So you can separate the two in your emission cubes. That also allows you to actually compute the XCO conversion factor as a function of galactocentric radius, right? So you have, actually, I'm going to just skip over that because I think I'm going to run out of time. But basically, if you have 12 CO and 13 CO, you can get your XCO factor. And we did that and mapped it out as a function of galactocentric radius. And what you can see is XCO basically is, about 2 times 10 to the 20 around the solar neighborhood, and then increases as you go to the outer galaxy. So one important factor, as I said, you have this denser molecular gases traced by 12 and 13 CO versus more diffuse envelopes that are only detected in 12 CO. We've been able to map this out over the entire disk of the galaxy. And it turns out that in the inside the solar circle, so below a distance, a galactocentric radius of 8.5 kiloparsecs, the fraction of dense to diffuse gas is high. So you have more dense gas, less diffuse gas. But as you go to the outer Milky Way, right, basically it's 50-50. So you start having a significant contribution of diffuse molecular gas to your CO emission. Now, if you map things phase on without having to assume axisymmetry and plotting things in 1D as a function of galactocentric radius, you get this kind of map. So again, using those 3 surveys, GRS, outer galaxy survey, and thrums. So this is the surface density of molecular gas traced by 12 and 13 CO, face on, out to about 10 kiloparsecs. The outer galaxy survey goes a little farther. But basically, you can start to see some structures, right? You have these dense areas on the galactic disk, which is some of what we've associated as spiral arms. And again, the coverage is not sufficient to really pin down the spiral structure of the Milky Way. But this is I would say, using the most up-to-date surveys and no assumption on the CO conversion factor, so using 12 and 13 CO, which is kind of the most complete picture that we can get. The diffuse gas in the Milky Way is relatively uniform over the disk, as opposed to the denser gas, which again may follow some kind of spiral structure. I'm gonna skip that. So what is this diffuse gas? So you can see an integrated intensity of the diffuse and dense gas components that we've identified using 12 CO and 13 CO. This is in the outer galaxy to try to avoid confusion. So again, in the inner galaxy, you may have several clouds along the light side. So if you look at integrated intensity, you're mixing things up. In the outer galaxy, because the density of molecular gas is much less, the integrated intensity really gives you a slice towards mostly single clouds along the light side. But what you can see is this diffuse CO emission is really coming from the envelopes of molecular clouds. You can see the denser parts that are seen both in 12 and 13 CO in red, and the blue parts that are only seen in 12 CO on the outside really trace the envelopes. So again, this may not be star forming, but it's contributing to the CO emission. So it's important to understand those two contributions to better relate the fuel that is used for star formation in the form of molecular gas versus the star formation rate, as many studies do. Now, can we use CO emission on the galactic plane to trace the spiral structure of the Milky Way? And what I'm going to say here is just, this is very tricky. First of all, you have limited coverage in a lot of the surveys. You can only see a small chunk of the Milky Way. But even when you have the whole plane, you have observational biases, right? You're going to have bigger clouds at farther distances just because you can't break them up due to limited spatial resolution. You have the kinematic distance is not perfect, and so you end up with these artifacts like you can see the tangent point here. Basically, it's throwing out clouds at those velocities towards slightly or shorter or smaller or larger distances. So you have these artifacts, empty points here. It's very difficult. So people have tried using H2 regions, catalogs of H2 regions, H1 and CO maps to pin down the spiral structure of the Milky Way. This work by Hu et al. 2009 tried to make some fits to the distribution of H2 regions and molecular clouds. And they found that they had a poor fit with 2 arms, but better with 3 and 4 arms, but they basically could not differentiate between 3 and 4. So this is really tricky and perhaps impossible. There's recent work by Josh Peak teams that looked at the Perseus arm in detail using masers. So you can see here again, a velocity longitude diagram with the Perseus arm in green here. This is the velocity you would expect for this arm. The masers are shown as green points here, and then the molecular clouds associated with the Perseus are the orange points here. And you can see that the structure is pretty well defined in LV space. What they did then is that they took 3D dust maps to actually measure the actual distances to molecular clouds that are associated with the Perseus in LV space, and found that, in fact, when you look at the Perseus face on, so using distances from 3D dust maps, which are not affected by, say, streaming motions of velocity crowding that may pike points here in LV diagram together as a kind of an artificial structure. In fact, the Perseus arm is not seen when you look at the disk face on using distances from 3D dust mapping. And so what's happening here is you have some kind of velocity crowding in LV space that gives you the illusion of having a spiral arm there, when in fact, when you look at the face on disk deprojected using accurate distances in 3D, there is no arm. There's no overdensity in this arm. So, using velocity, PPV cube velocity to map out the spiral structure of the Milky Way is very tricky because of non-circular motions, streaming motions, etc., that may actually give you the illusion of spiral arms when in PPP space, they are not there. So open questions. How do we retrieve the 3D structure of gas in the Milky Way from emission line cubes? Again, this is the distance problem that I talked about. How do we probe molecular cloud dynamics? I think the 3D dust mapping combined with line emission cubes like CO will really help with that. And what is the structure of the Milky Way molecular gas? Again, we're limited by uncertainty on distance, so this is really hard to do. So I'm going to talk about turbulence in molecular clouds now, because I think turbulence is really a driver of the formation, evolution, dynamics of molecular clouds, but also star formation. Molecular clouds are inherently turbulent. I don't think I need to convince you too much of that, but basically if you look at simulations that include the major physics like gravity, turbulence, magnetic fields, and jets, you can see that molecular clouds are really transient entities that morph into new clouds and evolve on, a dynamical timescale, which is about 1 million years or so. So it's constantly reshaping, full of flows. And so, in this context, how can you identify molecular clouds as individual structures and derive things like a virial parameter? it doesn't make complete sense when you look at the big picture and the turbulent nature of molecular clouds. So let's look at what we know from observations and simulations on the turbulent properties of molecular clouds. So the first thing I wanted to point out, as I said, kinetic energy is often interpreted as a source of support against collapse in molecular clouds, but actually that's not always true, right? So when you have a velocity field, which is dominated by turbulent motions, which is, driven on large scales, dissipate on small scales, you can have different modes of kinetic energy. So your forcing can be diversion-free, and that's called solenoidal forcing, which is basically, more rotational. There's no compression or expansion. You can have compressing forcing, which is, a divergence that is greater than 0. So compressive would be, for example, a supernova shell expanding into the ISM. It will compress the edges. And you can have also expanding forcing, which has a divergence greater than 0. So depending on the type of forcing that you have, the morphology of the clouds that are resulting from that are very different. On the left here, you have solenoidal forcing. So you can see that the density enhancements are not too strong and it's still pretty diffuse, versus compressing forcing here that really leads to strong density enhancement in molecular clouds that may lead to star formation, because you have those over densities that can become over the gene's mass and then collapse. So, depending on whether you're looking at a velocity field that is solenoidal or compressive, the role that the turbulence and kinetic energy plays in the collapse of molecular clouds or support of molecular clouds is very different. So I'll go quickly over this, but the mathematical translation of this is that the density distribution of clouds, depending on whether you have compressive or solenoidal forcing, will be very different, right? So this is the density PDF for a compressive forcing simulation versus solenoidal forcing. You can see that the compressive forcing has a long tail at high densities, which are these density enhancement that we saw in the simulations. And then these are all log normal, approximately log normal distributions that you get from isothermal turbulence. And the width of the density PDF will depend on the Mach number of the driving of turbulence, but also on this B parameter. And this B parameter is the one that is different depending on whether you have solenoidal or compressive forcing. So for compressive forcing, you have a B of 1. And so your velocity, the width of your density distribution will be much wider. For solenoidal forcing, B is only 1/3, so narrow distributions. There have been attempts to measure this B parameter in actual observations. The Ma 2022 paper is one of those. So they went ahead and measured the column density probability distribution function in molecular clouds, and then plotted it as a function of the Mach number, which they got from the velocity dispersion. And in this case, they found a B of 0.76, which would be somewhere in the middle between 1/3 and 1, so solenoidal and compressive forcing. There's been other attempts to measure the detailed density distribution in molecular clouds. And I just wanted to point out that, yes, from turbulence, we expect a log normal, but the effect of gravity can introduce a power law in the density distribution of clouds, which you can see here in 2 measurements. These are infrared dark clouds, and then this is the molecular cloud plus infrared dark cloud within it. So gravity can introduce power laws in the density distributions. Now, so this covers kind of the density distribution. What are the effects of different types of forcing, different types of turbulence on the energy spectrum of molecular clouds? And so the energy spectrum is basically the velocity, the kinetic energy. So for Kolmogorov turbulence, it's incompressible with a Mach number of 0.3 or less. You have purely Kolmogorov turbulence. So you can measure the energy spectrum through the velocity field. And so this is the theoretical basis, right? The U is your velocity. This is your energy spectrum. And for Kolmogorov turbulence, the exponent of the energy spectrum is 5/3. You can also characterize the velocity field using a structure function, which for Kolmogorov, the second order structure function would have an exponent of 1/3. And in this case, which is incompatible, the dissipative structures are filaments. Now in AISM, I think we've already talked about this, but motions are supersonic. And so in this case, you don't have Kolmogorov turbulence, you have what we call Burger's or Kolmogorov-Burger's turbulence. This is supersonic and compressible, and so the exponents of the energy spectrum and structural functions are different. In particular, the slope of the power spectrum or energy spectrum that we expect from supersonic turbulence is 1.74 as opposed to 1/3 for Kolmogorov turbulence. And in this case, the dissipative structures are sheets. And so this was already shown by Stephanie, but it kind of gives you the big picture of what's going on, right? So you have the sonic scale at which the velocity dispersion is equal to the sound of speed of sound. Above the sonic scale, motions are supersonic. You drive turbulence on large scales, and then you cascade down to smaller scales. Your turbulence spectrum will have a slope of 0.5 above the sonic scale, and it will be lower below that because you have Kolmogorov's versus Burger's turbulence. And then you dissipate the energy on small scales. This is very difficult to measure because, as I said, you have access to PPV cubes, not PPP cubes. You don't know your 3D velocity field. Some scientists have derived statistical methods to try to extract the energy spectrum of turbulence, in particular looking at the power spectrum of integrated intensity versus individual velocity slices in PPV cubes. There's a lot of math involved, but this has been applied to Perseus observations in 13CO by Padoan et al. 2006. And they found an energy spectrum exponent of beta of 1.81, which would be consistent with supersonic compressible turbulence or Burger's turbulence. Another method to try to get at that is principal component analysis, where basically you apply PCA to your PPV cubes, you extract principal components, and then you look at the relation between the velocity dispersion in each principal component versus the spatial scale characteristic of these principal components. And you get a power law that has a slope, depends on the molecular cloud. But if you aggregate all molecular clouds in the GRS together, basically you get a PCA slope of 0.6. Now it's unclear what this PCA slope exactly is because we're not actually measuring any structure function or energy spectrum. And so what we did is we actually used hydrodynamic simulations to calibrate this relation and found that the power spectrum of turbulence is related to the PCA exponent using this relation. And then from that, we were able to conclude that the turbulence that we observed in CO observations of the galaxy is consistent with a beta of 1.9, which is basically Burger's turbulence. I'm going to skip that. Open questions on turbulence. So the main one is really how do we measure the turbulent properties of molecular clouds? And I think we alluded to that previously already, but we don't have access to the 3D velocity field or the density field statistics without the PPP cube. And so we need to come up with metrics that can distinguish between different models or simulations. The power spectrum is not enough, and the phase information is actually really important in the ISM. Because it conveys basically the solution to MHD equations, right? You can simulate a fractal medium with no hydrodynamics at all that will have the same power spectrum that you observe in the ISM. But a lot of the hydrodynamics is captured in the phase of the power spectrum. And then what are the mechanisms injecting turbulence in molecular clouds? We just don't know. We know it's driven on large scales, but whether it's shear or supernova explosions or other instabilities is completely unclear. I think I need to conclude in like 5 minutes, 2 minutes? 2. Okay. All right. this is basically putting it all together, using, looking at gravity, turbulence, magnetic field, and feedback in setting star formation in the Milky Way. This is a simulation by Christoph Federath that includes individual physical processes, so gravity only, gravity turbulence, adding the B field, and then feedback. And obviously you can see that only the last one looks pretty realistic. You form stars way too fast in the first one. And you really need the support of the B field, you need the turbulence, and you need the feedback to get realistic star formation rates. I'm going to skip over that and just look at traces of star formation, specifically in the Milky Way. And in particular, what we can do in the Milky Way is use young stellar objects to trace star formation, because we have the resolution, we have the detail to be able to basically count new stars. So star formation in the Milky Way is observed in those filamentary structures that may be sheets that we see in projection called infrared dark clouds. They were traced by Spitzer and Herschel. And so you trace basically protostars forming in those RDCs using mid-infrared emission, like 24 microns, but also dense gas tracers, line emission like HNC, HCN, ammonia, etc. YSO counts in the IR provide an estimate of the star formation rates on timescales that go from 1,000 years to a couple of million years. And this is obviously a resolved star tracer. So what Tom Robitaille and Bob Whitney did is they actually measured YSOs in the Milky Way, modeled their spatial distribution, and came up with a star formation rate of roughly 1 solar mass per year for the Milky Way. You can also do this using a Herschel at longer wavelengths to get kind of photostellar cores and count them. And this was done in the ELIA 2022 paper. And they did manage to actually deproject the star formation rate surface density in the Milky Way, of which you can see a map here on the galactic plane. So this is surface density of star formation rate. And they did try to map out that enhancement in star formation rate from known spiral arms from previous modeling. But basically, star formation rate in the Milky Way depends on galactocentric radius, and just like the molecular gas, peaks around 5 kiloparsecs and then goes way down as you go to the outer galaxy. This is a compilation of different star formation tracers in the Milky Way. So mostly YSO counts on the bottom here. You can also use free emission to calculate the star formation rate in the Milky Way. This was first done by Kennicott et al. And basically they modeled the number of ionizing photons that you need to sustain the number of H2 regions that you see in the Milky Way using free emission. And also came up with a star formation rate similar to the YSO counts of about 1 to 2 solar masses per year for our galaxy. I would note though that free probes timescales longer than YSO counts, so 5 to 8 megayears, because then you're looking at actual H2 regions, not embedded star formation that the YSO counts probe. I think this is my last slide. I just wanted to say there's a really cool study by Catherine Zucker that actually modeled the propagation of star formation in the local bubble. So the local bubble is a bubble of ionized gas near the sun. And they went back and looked at known star formation histories in the area. They looked at 3D dust mapping, and they looked at proper motions of star forming regions, and were able to explain what exactly happened in the last few gigayears in the solar bubble. So basically, you had some supernova explode. These had an expanding shock that hit some gas that was previously there, compressed this gas and pushed it outside, and which resulted in several star forming regions around us. And the 3D distributions and proper motions are consistent with this explosion, as well as the mechanical energy that was needed to push the gas out and start triggering star formation. So if you want to read more about this, you can go check it out. There's actually a 3D visualization of the star forming regions around the local bubble. It's pretty cool. You should really check it out. And I think I'm done. Almost. I'm going to skip that because this is really extragalactic. And yeah. All right, open questions in terms of star formation in the Milky Way. Well, I mean, I'm going to ask the same question as Danny previously asked. I think it was you, Danny. Yeah. What are the star formation processes, and does one process dominate over another in different environments? What are the timescales for star formation? I mean, basically, yes, we write all our proposals using some of these sentences, and different processes may dominate in different types of environment, like the galactic center, spiral arm versus interarm environment. And I think I'll stop here because I'm way out of time.
All right, thank you. We did have 10 minutes from before, so
Yes.
it's up to people. Yeah.
Thank you for the talk. So I saw a subliminal slide relating the star formation to H2. And in the first part of your
This one?
talk, you didn't mention the cooling by H2.
Yes, there is cooling by H2, although I think it's not dominant over C2 or O1 or CO in molecular clouds even, right? So the dominant cooling will be C2 and O1, and then when you get to denser parts, CO as well. Yeah.
Thank you. So I was a little spooked by your discussion of the CO dark gas at the start and the fact that it's such a large fraction of the molecular gas mass.
Mm-hmm.
So when we're looking at these molecular gas mass derivations, should we be interpreting those as kind of lower limits or just with very large error bars, or how can we think about all of this missing mass?
Right. So lower limits, or I would say probably lower limits, not just because of the CO dark gas, but also, as I said, because the segmentation methods does not always capture all the emission that's there. You know, and we also have to make assumptions, even when you have 12 CO and 13 CO, for example, to get the excitation and the column density, you still have to assume like a 13 CO to H2 abundance ratio, right? That can vary depending on where you are on the galactic disk. So I'd say it's both error bars, but also lower limit because of CO dark H2. But again, I think we have not solved that problem of CO dark H2. It's still, I think, unclear exactly what fraction of the gas that we probe with CO is what fraction of the total molecular gas mass is posed by CO. I think this is still very controversial because of the circularity with dust to gas ratio, basically. So you can use dust to trace the gas, but then you have to assume a dust to gas ratio, and we don't always have the, I think, correct prescription that accounts for dust growth in the ISM in particular. The gamma rays help with that, but there's still some limitations. I don't think we're too bad shape in the Milky Way. The low metallicity universe is definitely struggling much more with this limitation of CO than for people studying the Milky Way.
So quick follow-up, sorry. On that note, I was just wondering, when you when you show the updated Larson's relation, you say that the mass is less than virial.
Yeah.
So then the cause is on the infall. I was wondering how much of the limitation might be affecting that. Do we really need additional support to?
Right. Yeah.
Okay.
So right. So I think there, the CO dark gas is not biting you too much because you measure the kinetic energy from the velocity dispersion and the mass from the emission.
Okay.
And so you aren't right, like if you have additional CO dark gas, it will not contribute to sigma and it will not contribute to M. So I think that's not too big of a problem.
Where were the hands?
Thank you for the great talk. So since there are like different algorithms for finding structures, how much variation is there like in like the physical space, like that the clouds occupy using different algorithms, as well as like the properties of the clouds, like how much systematics we have to account for?
Yeah, so algorithms that clump find tend to leave quite a bit of emission out. So basically for example, your surface densities might be a little bit higher than if you use a Gaussian decomposition plus clustering algorithm, just because you're going to be capturing more diffuse emission with the latter. So you're going to have lower surface densities, larger radii. And so, yes, the properties definitely depend on your segmentation method, also on your tracer, because if you're just using 13CO, you're also probing the kind of denser inner areas of molecular clouds as opposed to, say, 12CO. And so, yeah, we have to keep in mind that any statistical properties that we derive depend on the segmentation algorithm and the tracer.
Oh, actually, my question is quite similar to hers, but since 12CO is more optically thick, and 13CO can kind of trace the denser inner part of the molecular clouds. So, like, if we want to see the hierarchical structures of the cloud, maybe 13CO is a better tracer in this sense, or?
I mean, it's a pretty decent tracer, I would say. If you want to capture the entire hierarchical structure, you do need to go down to very diffuse levels, though. And so we have been able to constrain the turbulent hierarchical property of molecular clouds using 13CO only. But again, what you derive depends on your tracer. So I would say the same is applicable to the kind of hierarchical structure studies as well. And people have used H1 as well for, in external galaxies in particular, but also in some star forming regions in the Milky Way. Like they measured the power spectrum of the density, the integrated intensity of the emission using H1. So there are things you can do. You just need to be aware of, the model dependencies or tracer dependencies, I would say.
Hi, great talk, thank you. So also a similar question to the last two. You must be aware of the Gauss clumps algorithm that has a little different approach with respect to clustering. So it uses Gaussian spheres. Basically, it fits Gaussian spheres or ellipsoids actually to the peaks or in the intensity distribution that we have. So I think it performs a bit better in terms of PPV cubes, and in these kind of algorithms like clump find, it appeared to me at least that it is a bit biased in terms of the observation that you get. So if you have a line of sight intensity distribution that so in clump find it's really biased in terms of what threshold you give to it, right, to detect the structure, and that makes it harder because the structure is not really conforming, not really detecting, for example, sometimes the faint emission.
Correct. Yeah.
So how would you balance these problems, and how would you go about it? Yeah.
Right. So yes, the just regarding Gauss clump, I think the one limitation of the Gauss clump is it does assume, ellipsoid shapes. But in any case, I think if I were to redo all of this now, I would probably go towards a Gaussian decomposition plus clustering analysis, like Marc-Antoine Miville-Deschênes did, because to me, I think the most important is try to capture as much emission as possible from the PPV cube. As you say, clump find leaves quite a bit out. In fact, I think I have a plot of this. Let's see. I do want to show this because I think it is important. I have it right here. Almost, yes, okay. This plot, I didn't mention it, I didn't have time, but like, so here I plotted the, dense and diffuse CO gas. No segmentation algorithm here. This is just from the PPV cube. And then you have the surface density of molecular gas that's only included in molecular clouds. And you can see that, this is a log space. So that's a factor of several, maybe an order of magnitude here between what is captured by confined and the actual total that you get from the PPV cube itself. So I think if you're trying to really map out the distribution of molecular gas in the Milky Way, like we need to do away with these segmenting algorithms altogether. Just work with the PPV cube.
Hi. So I have a question actually related to this one. So to the specifically to the dense to total ratio, maybe a naive question, but why would I expect this ratio to increase so much towards the central regions? Is it because only dense enough substructure can survive that environment, or?
Right, you mean towards the galactic center?
Yeah.
Yeah, so basically the molecular gas disk becomes just much denser. There's molecular gas everywhere. And so the envelopes of clouds aren't quite as exposed as say in the outer galaxy where, your clouds are much sparser. And so the kind of the connective gas between different structures is farther apart, more diffuse. And at some point towards the galactic center, you start getting clouds, coalescing together. And so there's not much space for very diffuse gas. It's just a much denser gas disk.
All right. And just clarification. So in the center, the star forming efficiency is higher, right?
In the very center, it's lower.
Why is that?
So I'm talking about like CMZ, okay? There's different scales. Towards the, right, are you talking about towards the galactic center as relatively low galactic? Because the CMZ is a completely different business altogether, right? Like the central molecular zone has a low star formation efficiency probably because of very turbulent motions. In fact, also motions that seem to be dominated by solenoidal divergence free motions that, like shear, that basically prevent collapse. So you have a lot of molecular gas, but the star formation is pretty high, but it's not high enough to explain this high molecular gas mass. So that's the CMZ. Now, towards the galactic center, if you're talking, 1-2 kiloparsecs away from the galactic center, then I think the star formation efficiency is, I mean, the bar does have some effect, so it might be a little low. I'm not sure, actually. I would have to look.
Okay.
I don't know if somebody's made a map of SFE versus the galactosonic radius.
Thank you.
All right. I thought maybe I could come back to Patrice's question earlier and also tie to one of your remaining problems about star formation. I thought at the beginning, the formation of first generation of stars, when there's no metal, cooling must be driven by H2. Since there's
Yes.
no CO.
Yeah. I mean, I would think. But even forming H2 in those environments is hard, right?
That's right.
You have to go through the gas phase.
Hence the mystery of forming the first generation of stars.
Yes.
Any other questions? Oh, yes. Maybe last, so we can head to lunch.
I was wondering if you could expand more on like the filaments versus sheets, because I feel like we hear a lot, we see a lot of filamentary structure, but I never actually see any examples of sheet structure. And is it just a projection effect, or do we have actual concrete evidence, or is it all through simulations, stuff like that?
It's a lot through simulations. I don't have the reference, but I did have a discussion with Josh Peak once, who mentioned that if there were sheets, they were more likely to be aligned with the galactic plane, in which case we would always see them in projection as filaments. I can track down the reference with him, but I'm not sure on top of my head what that was.
I can also just ask him.
Yeah.
All right, let's thank the speaker again.